Okay, hi Jana, good morning. So thank you everybody for accommodating my request for this last minute change due to some personal dependency this weekend. So today and tomorrow we are meeting at 10 o'clock and then we'll go back to our original schedule from the following week. So only for 2 days I need everybody's support. So what we are going to learn today? And before I start, see, in the year 2026, the resolution that I have taken for myself and for all of you is that we'll put a little bit more emphasis on practicing what we learn in the class. Okay. So my request to you all would be, whichever unit we are learning right now, after the unit is done, please spend 15-20 minutes to straight away jump onto the unit test in Khan Academy for the respective topic and try solving those problems by yourself, assuming that you have understood the concept. If you are struggling, catch hold of the teacher, he is the culprit. If you are struggling, okay. So I'm not asking you guys to do assignment as an element of pressure. Rather, I want you guys to use that as an opportunity for challenging your teacher. That okay, you explain something that is not good enough for solving these problems. Okay. Does that sound okay? Make you guys feel better? That you always have a chance to challenge your teacher rather than feeling bad for yourself when you are not able to do something. It's always the teacher who is the culprit. The teacher is not doing his job right. Kids will have problems solving things. Okay, so today let me not rely on my memory and say something. These are the things that I have planned for today. I mean this week basically. So we will. This is again unit 12 of Khan Academy where we are doing advanced math at advanced level, which is basically advanced level of algebra. And then following this we'll have advanced geometry and trigonometry as the next unit or the last unit, and then we'll go back to the same cycle. So in this one we talked in the previous class, if you remember, we talked about how do you factor quadratic equations and expressions and polynomials. And then in the same unit, we are continuing with the next topic, which is around dealing with rational and radical exponents. As part of that, we will talk about exponent rules, adding, subtracting, multiplying, dividing different types of exponents, and then negative. What is the negative exponent? How do we deal with operations with rational expressions? So first thing first, radical and rational exponents. Be very honest to me and tell me who knows about it. Have you heard about it? And what is your understanding of it? If you have to explain that to me in simplest term, how would you describe that to me? What is rational and radical exponent? Yes, Pranay.
So rational exponents in this case means that are like fractions or all rational numbers, and then radical or is the same thing as rational exponents, but they're expressed as radical.
Okay. Anybody in the class who has a different way to express this or describe it? No? Don't be shy, guys. I know it's early morning, you guys would have just woken up. Some of you might not have brushed your teeth also. But again, I'm not trying to put anybody on the spot, but see, the question is, are you guys clear about what Praneeth said? Or do you have a different point of view? Vivan, Vishal, Jenna, Yasmita, anybody? No? Okay. So, as a normal practice, I will go from the scratch. First of all, is everyone in the class very, very clear about what is exponent? Jenna, Smita, Vivan, Vishal, everybody? Okay. So I will probably muddle the water a little bit. I will look at the basic concepts, we'll talk about it, and then we'll jump on to what is radical rational exponents. So some of the things that I'll say which will sound very kiddish, rudimentary to you all, bear with me because these are the backbone. If I ever talk about an exponent, essentially what we're talking about is something to the power something. 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 These are all exponents. When you look at x to the power 5 or 3 to the power 5, 2 to the power 9, 7 to the power minus 9, all these are different exponents. Now, what are the key elements of it? When you see this one, this is your base. 7 is your base for this exponent. This x is your base for this exponent. 3 is the base for this one. And these are the powers or the exponent. So basically when you represent a number in this form, it's called, when you represent something where something to the power something in this form, this is the exponent form. And you guys will say, you are getting really too old, you are repeating yourself. And that's okay. This is the year when I'm turning 50, so I have all the reasons for being old. Now, so if I say 3 to the power 3 or let's say 5, in simplest form, we say it is nothing but 3 getting multiplied by itself 5 times. This is what you all know. So whatever we had here when we were wasting a lot of ink and space on the board, we had a short form of representing it, and this is the exponent form. So this let's say tomorrow if you have to multiply 3 with, or let's say 5 with itself 200 times, my marker will give up and it might run out of ink, but I can use an easier method for writing it down without stressing out my marker. Correct? Everybody with me? So there are 3 key rules of exponents, which is the backbone of it, and this is going to remain with us for the rest of our life as a very handy tool. So let's look at it. What are those rules? And again, I repeat myself. These rules you guys know for sure. I'm repeating that because that will come handy for us when we are dealing with radical and rational exponents also. X to the power a times x to the power b is nothing but x to the power a times b. Sorry, a plus b. X to the power a divided by x to the power b is nothing but x to the power a minus b. X to the power a in parentheses to the power b is nothing but x to the power a times b. Does these rules sound familiar to you all? Jenna, Vivan, Yasmita? Yasmita, okay. Vivan is still thinking what to say. Does this rule sound familiar to you all? Okay. Now, I'm not going to go into the detail of it, why these rules are true, because we have talked about that in the previous classes, but if anybody has any doubt, raise your hand. Otherwise, in the interest of time, I will not go into proving these rules for now, because we have done that before. Everyone? Yeah. Okay. So here, these rules, how these rules are derived, it's very easy. We have done that in the past, so I'm not going to that. Is that okay? Or anybody wants me to double click on this? You guys are fine? Okay. So, these are the rules. These are the rules of exponents. These are the 3 key rules of exponents that should remain in our back pocket for any calculation hereafter. Keep these rules with you. First rule says when you are multiplying 2 exponents with the same base, your power gets added. When you are dividing one exponent by another one and both of them have the same base, the resultant would have the power, which is a subtraction of the denominator's power from the numerator's power. Gloria, good morning. So basically today we are talking about radical and rational exponents. While you are late by 11 minutes, but good news is you have not missed anything. And again, like I thank everybody for accommodating this request. For today and tomorrow, we'll do it at 10 o'clock because of some personal dependency I have. My family is traveling to India today, and my daughter is going to college tomorrow. So that's the reason. Okay. So only for today and tomorrow, and then we'll go back to our original schedule. So here, the three rules of exponents, I was just kind of repeating that when you're multiplying two exponents, your power gets added. When you're dividing one exponent by another exponent and the base is same, power gets subtracted. And when you have an exponent in parentheses and then you have a power on that. So basically it's like double dose of exponent, your powers get multiplied. So this is a basic rule of exponent. Now we are going to the next level where we are trying to talk about what is radical and rational exponents. Answer is very simple. Let's talk about rational exponents. Here, here A and B we have. We have assumed the power as A and B here in the rule. Nobody is telling that what is the value of A. Value of A could be 5 and value of B could be 2, or value of A could be 1 by 3 and value of B could be 2 by 5. Nobody is stopping us from that. So here A and B are real numbers. You can choose what number you want to deal with. What I'm saying by that is essentially you can use the exponent rules for dealing with situation like this also. Same rule of exponent. When we start discussing about exponents, I gave the example of natural numbers 1, 2, 3, 4, 5, 6, 7 kind of thing. But that doesn't stop us from using fractions as the power as well. And when you have an exponent in this form, where the power itself is a rational number or a fraction, that is why it is called rational exponent. Okay? Does that sound okay to relate? So now, let's do a jump start. If I asked you guys to find out can you guys do it real quick for me? I want to see how comfortable are you guys with the basics, and then I will jump on to the next steps. Just a clue for you all is, these are three exponents in the rational form. And what I'm saying is, if you know the rule of exponents, you can apply in the case of rational exponents also. You are not going to get any new set of rules for rational exponents alone. We will leverage what we already know. So my best attempt is, I will try to minimize the number of problems that I bother you for.
Is this the regular one or 2 9?
2 9, 3 4. So 7 to the power half times 7 to the power 2 9 times 7 to the power 3 4. Deal with it. I'm giving you guys 2 minutes, and till that time I'll be muted. Hi Neil, good morning. Yes, Praneeth, what did you get? 7 to the power 53 over 36. Okay. Yes, Neil, you joined a little late because of me. No worries, Vita. I know I am troubling kids to wake up early on a weekend, but just please accommodate this request for today and tomorrow. I have some personal dependency. Okay. So we are talking about rational and radical exponents, and we have talked about exponents in the past. So I just, before you join me, I just reiterated those rules of exponents, and I have given, and I said that same rule will apply for rational exponents also. What is rational exponent? When you have exponents such that the power of those exponents are rational numbers or fractions. That is why they are called rational exponents. And we can use the same set of rules. So just to give a jump start, I have given this problem to all of you to solve, and Praneeth has given me some answer which I don't remember. but I want everybody to give it a try, and then we'll go on to the next steps, because this is just a building block, stepping stone rather. I'm giving you guys other yeah.
I got 7 to the power 79 by 36.
Okay, see, that is interesting because Pranit and Vishal both have got different answers. That's an opportunity for me. Okay, let's see what everybody else gets. I'll give you guys 1 more minute. Okay? Riya, Juna, Smita, Vivan, Need. I'm sorry, Vita?
I'm still working on it.
Okay. Yes, Juna.
I got 21 to the power 53 over 36.
That is interesting.
I want to change my answer.
Hmm.
I got 7 to the power 27 by 36.
Okay. So I'm still getting different answers, which is good. That is fine. We all have done keeping certain assumptions in mind, and when I will solve it in my way, at least we'll try converging to one way of doing it. In a minute, I'll get started. Okay. Shall I? Okay. So all of you who have So all of you who have solved it or who are solving it, now see your teacher doing it in the simplest possible way. Okay? I'm applying RAN technique like I always do. Read in the question 7 to the power 1 by 2 times 7 to the power 2 by 9 times 7 to the power 3 by 4. So I have 3 exponents to be multiplied, and as the question says, based on the value I see, these are rational exponents. Nothing different from how an exponent will behave. This is by reading. Now I'm analyzing. So when I'm multiplying 3 exponents, same base, oh, my power will just get added. So result of this would be 7 to the power 1 by 2 plus 2 by 9 plus 3 over 4. That's it. And for everybody who is thinking, right, that you gave the rule where you are multiplying only 2 exponents and here we have 3. It's okay. I'm still not cheating you guys. I'm still not bluffing. Okay? Let's do it this way. Let's look at it this way. These two together, 2 things, and then the third one. When I am doing this one, this will become 7 to the power 1 by 2 plus 2 by 9. And then I am multiplying that with another one. Ultimately, my power has to get added as long as my base is the same. So that is why I was saying that this one, and this one will get added. All will get added. We don't have to do any multiplication or factorization here. You guys agree with me? Everybody? Jana, Vishal, Riya? Okay. So basically, when I have any number of see, though this rule says 2, but as long as you have same base, you can simply go on adding all the powers together. Here we have 3 numbers. Tomorrow if you have 5, you will not even worry about all this that I was doing here. You will say my exponent rule is fine, I can just go on adding all the powers as long as my base is the same for all the numbers. So eventually this will result into 7 to the power 1 by 2 plus 2 by 9 plus 3 over 4. That's it. Once we find this one, we are good. So let's find out the value of this guy. 1 by 2 plus 2 by 9 plus 3 by 4. And I'm just doing a nursery recap for you guys. When I'm adding 3 fractions, I will find out the LCM of these numbers. The denominators. Start with 2, 2 1s are 2, 9 doesn't come in the table of 4, 2, 2 2s are 4. Next smallest number is 2, 1 remains 1, 9 doesn't come in the table of 2, 2 1s are 2. Then next number is 9, 1, 1, 9 1s are 9, 1. All done. 2 2s are 4 times 9, 36. That is my LCM. Now start with the first number. How many times of 2 gives me 36? 2 18s are 36. Plus, how many times of 9 gives me 36? 9 4s are 36. Multiply that by the numerator, 2. Here we had only one numerator, so that did not multiply. Third one is here, 4. How many times of 4 gives me 36? 4 9s are 36. Multiply that with the numerator, this is 3. This became 18 plus 8 plus 9 3s are 27. Divided by 36. That is equal to 18 plus 8, 26 plus 27, 53 over 36. Whatever you got here, you will plug in here, and that will be your 53 over 36. Does it sound reasonable to everybody? Or I did something not easy to digest? Riya, Neil, Sara, Viman, Vishal, do you guys feel comfortable with what I did, or I got you guys more confused?
I understand, sir.
Okay. Vishal, okay?
Yeah.
So net takeaway from this is, if you have exponents with the same base, no matter how many of them are there, you will just add the powers. And we did a recap of what we had learned probably 5-6 years ago. How do we add fractions? Once we added them, we got some value. That is my answer. Okay? So this is on the basic of rational exponent. Tomorrow, same thing will work. If somebody says 6 to the power 5 by 3 divided by 6 to the power 2 by 9, you will not actually care much about it, because you know about the second rule of exponent, which says when you are dividing one exponent by another and both of them have the same base, eventually your resultant would be this. You will subtract the power of the denominator from the power of the numerator. X to the power a divided by x to the power b equal to x to the power a minus b. So, though we started our journey with the fact that these are the 3 rules of exponents and we were comfortable dealing with natural numbers or whole numbers, but then same thing was for fractions also. Imagine a situation where, see, there is no term called decimal exponents, but tomorrow if somebody says find out 10 to the power 0.3 divided by 10 to the power 0.1, you will say same thing, 10 to the power 0.3 minus 0.1. That's it. Yeah? Does that sound okay? So, in fact, we have invented a new term, decimal exponents. There is nothing called decimal exponents. You will not find that in any of the books. But what I'm saying is, as long as our basics are clear, this works fine. You can apply it on any of these things. Okay? So, is everybody okay? Everybody awake now? Yeah? Okay. Riya, Priya, Sarah, Vivan, Neil, everybody okay, right? Isha? Yeah, okay. So let's look at some interesting problems. Applying these concepts and see how, okay. So we just looked at exponent rules. Let's look at some more concepts and then we'll come to some problems, okay. Next one is adding, subtracting, multiplying and dividing different types of exponents. Let's look at a situation like this. While I'm saying this is adding or subtracting exponents, actually we are dealing with polynomial operation. Okay. Let's say I have 5x to the power cube plus 2x to the power 9 plus 3x to the power 3 plus 7x to the power 8 plus 4x to the power 5. What we have is, this is one exponent, other exponent, 5 exponents we have. And when we are trying to add them, remember every exponent has its own identity. Meaning, every exponent has its own identity based on the base and the power. Now look at these exponents here. This guy, base, all of them have the same base, x. X is the base for all of them. But then, when you are looking at these exponents, only these two can be treated as like terms because they have the same base and same power. That is how these two can be called like terms. Okay? X to the power 3 and x to the power 3. You will not add this guy with this guy. You cannot add them because these two are different. Though the base is the same, but the power is different. And if base and power combination is not the same, it should not be treated as like terms. What I mean by that is, when you are dealing with this, what you will say is, I can add this guy and this guy together. Everybody else is different. Here x to the power 9, x to the power 8, x to the power 5. So, as a result of this whole thing will become 5x cube plus 3x cube. 5 plus 3x cube, 8x cube. These two are taken care. Then plus 2x to the power 9 plus 7x to the power 8 plus 4x to the power 5. All these terms are very different from each other because though they have the same base, but there is no way you can put them together. They have different powers. At best, what you can do, you will say, what is common among all of them? See, x to the power 3. This power is common among all of them. What I am doing is, when I take x to the power 3 common here, it becomes 8. In this case, when I take x to the power 3 common here, 2 is not going anywhere. X to the power 9, I have taken 3 out of it. So this becomes x to the power 6. And here 7 is not doing anything. X to the power 8, I am taking x to the power 3 out of it. So it becomes x to the power 5. And here 4 is not doing anything. X to the power 5 becomes x to the power 2. And I'll give you guys 20 seconds to digest this. What I'm doing is, here in all the terms, I had x to the power 3. This is the smallest power that I could find common among all these terms. So if I take this thing out here, this one x cube is gone. So only 8. Here, you have power 9. You borrowed 3 out of it, which is a common term. GCF is what we call it, right? Greatest common factor. So out of 9, you took 3 out. So when you will multiply it to break the bracket open, these two powers will get added applying the first rule of exponent. When you look at this one, from 8 we borrowed 3 here, which is a common term. So it became 5. 5 minus 3 became 2. When you break the bracket open, you will get the same term back. Is it making sense to everybody so far or not? And it's okay to ask because I might be messing around, okay, based on how I understand things. But if anybody is not clear, let me repeat myself. So we had certain terms. We had, let's say, a polynomial with 5 terms. We are trying to see if we have a way to shorten it or simplify it. And the only way I can do is, I can only add like terms. So, when you're dealing with like terms or unlike terms, your definition is x, y being same term or like different terms. Here everybody has x common, but then when it comes to exponents, your like term definition changes a little bit. Saying your definition of like term would be derived based on the base and the power. If the base and power combination is the same, that only qualifies for being called a like term. So that's why you found only 2 like terms which you could add together. So this was the first concept. Second concept that you're seeing is, it's not GCF, greatest common factor. So essentially, we had this polynomial, we could factorize it this way. Because we saw that the smallest power of x, which is x to the power 3, is common among all of them. So we could take it out. And essentially when you're taking it out, you are leveraging your concept of first rule of exponent, which is this. Here from 9 you took 3 out. When you bring the bracket open, you will multiply them, it will become x to the power 3, 6 plus 3, 9, and 2 remains 2. When you multiply these two, it will become 7, x to the power 5 plus 3, 8, matching with this one. When you multiply this guy with this guy, it becomes 4 times x to the power 3 plus 2, 5. Yeah. So we learned how to, I would not claim that I taught you guys today. You guys know about it or knew about it. I'm just doing a recap of that. Is that sounding okay? So I will not go into the depth of these concepts again. What I'm saying is, when you have exponents to be added, you can only add the like terms. Likewise, when you have to subtract, you only subtract the like terms. You cannot subtract 2 oranges from 3 apples. Correct? So you will always look for a like term, and your definition of a like term has changed a little bit here. Okay. If the base is not matching, then forget about it. If the base is matching, then you are looking at the power or the exponent value to make your judgment. Okay. So that was on the addition subtraction. Same thing applies multiplication division. I will not even talk about it because multiplication division is what is covered in your rule of exponents. So let's look at 1 or 2 problems relating to this, and then we'll talk about some interesting gymnastic exercise, because morning time is for exercise, right? I will let you guys do a little bit of exercise. Everybody is thinking what this man is talking about. I'll show you guys what exercise I'm talking about. Let's look at one problem. I'm jumping. I will not jump. Let me stop a little bit. So we talked about exponent rules, we talked about rational exponents. And I started a conversation with radical exponent also. Radical exponent is not something that you would want to waste your energy for. Okay? Because radical exponent, let's see if I have 2 to the power 1 by 2. This is rational exponent because your power is rational number. I can write this thing as square root of 2. This is called radical exponent. So this sign that you see, that's a radical sign. So when you are representing your exponent in the radical form, it's called radical exponent. When you are representing your exponent in the rational form, it's a rational exponent. It's just some 2 different representation types. If I am saying 3 to the power 1 by 3, let's say 7 to the power by 3. I can write this in the radical form. This is the cube root of 7. I will write a small 3 here. So if you don't have something here, the default is 2. So this is second root, square root. When you are talking about cube root, you'll have to put an explicit 3. If you're talking about 9 to the power 1 by 4, you can write that in the radical form like this. You'll put a small baby 4 here, right next to it. Okay? I mean, make sure that you're not writing it here. You're writing it right next to the point where this radical sign starts. So that's explicit. So, Nothing means 2. Okay. So if you have to write, let's say 100 to the power 1 by 15 in the radical form, you will say 100 15th root of 100. That's the representation. Is everybody clear about the representation? So now our approach would be that whenever I have to deal with things in the radical form, I would rather think about that in the rational form. I'll probably convert or rewrite that in rational form, and then my calculation becomes much easier. Yeah? Because if we deal with this kind of situation, it might look a little daunting to begin with. So now, and that's the reason why, I would not claim that as a reason, that was a miss on my part, but somehow I forgot about radical form, describing the radical form to you guys, and I was thinking that okay, I'm done, let's do some problems. Now let's do some problems. I have, okay, I think this marker is running out of life. I have 2 times this times 2 of 2. It says, what is the value of the given expression? 2 cube root of 4 times 2 cube root of 2. What is the value of this expression? And the options you have are 2, 6 cube root. Second one is 4, 8, 6th root. Third option is 8. Fourth option is 16. So we have an expression 2 third root of 4 times 2 third root of 2, and you guys have to find out what is the value of this one, and you have 4 options. I want you guys to stretch your neurons a little bit and see what you are leaning towards and how you are thinking about it. That is more important for me. Okay. Somebody getting a wrong answer, I don't mind. My only goal is to navigate you guys to think in the right direction. Did everybody get the question in the first place? Praneet? So these are the 2 values I have. Okay, this is the expression we have. Okay? 2 third root of 4. Okay, times 2 third root or cube root, whatever you call it, of 2. You have to multiply these 2 numbers and see which of these 4 options would be your result after multiplying these 2 exponents. Yasmita, Jenna, Vishal, Praneet, Priya, Sarah, we want to try, right? See, trust me, these are the problems that make me younger by at least 30 years. Yes, Neil.
What's the first one?
Two times cube root of 4. Second term is 2 times, and this is our second term, second part of this expression is 2 times cube root of 2. Yeah?
Yeah.
Okay. I'll give you the
Which part is it to?
cube root of 4. 2 times cube root of 4.
Time 2 cube root of 2.
2 times cube root of 4 times 2 times cube root of 2.
Okay.
Good morning, Anya. I know, I feel bad for being an utterly bad teacher. Mhm. No, sorry, if only for today and tomorrow. I just need help from you guys for slight accommodation, and we'll go back to our original schedule. Okay. So right now, what we are doing is we talked about radical and rational exponents, and whatever we have learned with respect to exponents, we just did a revision of that, and then I explained what is radical and rational exponents, which I would want you to watch the video of the class to catch up on that. And I have given one problem to the kids to solve. Everybody will try. You also can try with whatever understanding you have, and then I will explain it. When I'm explaining it, I'll make sure that I'm able to explain to everybody. Okay. So I'll give you guys exactly 3 minutes. Okay. 10:42 is the time right now. 10:45 is when I will start bugging you guys. Enjoy your peace of mind for next 3 minutes. Yes, Praneet, what did you get? I'm sorry, sir? 8. Okay, we'll see. Jenna,
I got C.
you got C, that is 8. Okay. I will probably wait for 2 more minutes for everybody else to give it a try. Okay, so Jenna, you remember the day when you had come? That day we had a big storm in my neighborhood, and that apparently has damaged the roof of many of my neighbors. So if you're hearing some background noise, that is because my neighbor is repairing his roof. Till I have not come to US, I was thinking that the roof is built once and forever. It's only this country which tells you that you have to keep on repairing your roof. Every time there's something, there's a big wind, they'll repair your roof. There's a hail, they'll repair your roof. There's a heavy rain, they'll repair your roof. Unfortunate but true. Okay, alright. All that was unnecessary information for you guys to even hear about. So anybody apart from Praneeth and Jenna got the answer or close to being done? No? Okay. Then see your teacher doing all that he is supposed to do. So here, when I have to multiply this, again I am applying RAM technique so that I can copyright it for myself in future on the screen. So here I have to multiply, okay, 2 times cube root of 4 times 2 times cube root of 2. Okay. Radical exponent, that gets me confused. So I will write it in the form that I understand. Okay. So for Ananya, these are radical exponents. Okay. When you have this sign is called radical sign. This is a sign for radical. This is called radical sign. Okay. So here, when I have something like this, I don't feel comfortable. What I will do is I can rewrite that in the form that is easier to read. So 2 is 2, don't worry about it. 4 cube root of 4, I can write that as 4 to the power 1 by 3. That is what a cube root is. Anything to the power cube root means something to the power 1 by 3. If I say 8 to the power 8, sixth root of 8, I am essentially talking about 8 to the power 1 over 6. This 6 comes in the denominator. Okay. So, and this is a much readable number now. Okay, I don't have to deal with this sign. Times 2 times, again this is third root. So that is 2 to the power 1 over 3. Okay. So I have something that I can read better. Okay, let's first multiply these two. 2 times 2 is 4. This is okay. Then I have 4 to the power 1 over 3 times 2 to the power 1 over 3. Other thing that I would want to do is, see, we have learned the rule of exponent which says x to the power a times x to the power b equals x to the power a plus b. Okay. So Ananya, you can probably relate to it. We have covered that previously. Even if you forget, don't worry about 3 to the power 2 into 3 to the power 3 will be what? 3 to the power 2 is 3 into 3 2 times, and 3 to the power 3 will be 3 into 3 into 3 times. When you expand that, it became 5 times of 3, which will be nothing but 3 to the power 5. That is exactly what this rule says. When you are multiplying two exponents with the same base, your power gets added. Now, coming back to whatever was the option B, we will see. So, now we have two exponents, but their bases are different. So, first thing we want to do is make them the same base. So, 2 is a smaller number. See if I can break it to smaller number. I can write 4 as 2 square, right? 2 to the power 2. This whole thing to the power 1 by 3 into this one is 2 to the power 1 by 3. Okay? So now I have the third rule of exponent which says x to the power a to the power b equals x to the power a times b. Okay? So going by the RAM theory, we read the problem and we said, okay, fine. We have the information, then we are analyzing it, say, okay, fine. I don't want to deal with the radical sign. I want to convert that to a rational form. And then we should be able to deal with it. Once we convert it into a rational form, my thinking says that, okay, these two are exponents, but not the same base. So we'll convert that to same base and then we'll do the operation. That's what I'm doing right now. So we multiplied these two numbers, which were easy to multiply, and then we are trying to convert this to the same form, and then we'll see if we have a possibility of exploring it. So 4 became 2 square, and this whole thing to the power 1 over 3. So this, when I break it open, applying the third rule of exponent, All of you who joined late, who are not able to recollect, watch the video of the class, you will be able to catch up very quickly on that. Because this is not difficult, okay? So this becomes 2 to the power 2 times 1 over 3 into 2 to the power 1 by 3. Now we have come to a point where we have matching exponents. Exponents with matching base. Wonderful. 2 times 1 over 3 is nothing but 2 to the power 2 by 3. 2 into 1 is 2 by 3 times 2 to the power 1 by 3. Now you have two exponents with the same base, you will just add the power. 2 over 3 plus 1 over 3 will become 2 plus 1, 3 over 3. 2 third plus 1 third, 3 third, which is 1. So this power got added, it became 4 times 2 to the power 1 by 3 plus 2 by 3, which is 2 power 1. 4 times 2 is 8. That's what everybody got. Does it sound okay to everybody? Look at the journey from the beginning. You had expression in the radical form, you converted it to rational form, then once you converted to rational form, you saw different bases, you saw an opportunity for splitting that to a smaller number, and then that helped you get the same base. Then you are applying the first rule of exponent, of multiplication of exponents, and you got the power added, and here we are. Yeah? Yes, Pranit. Tell me what is that approach?
So I just checked that inside the cube root and I multiplied the two coefficients to get 4. And then I multiplied the cube root of 4 and cube root of 2.
Uh-huh.
4 times 2 is 8. Cube root of 8 is 2. 2 times 4 is 8.
Yeah, that's even. I think that is perfectly fine. So, in fact, that's a smarter approach, I would say. Okay, so that is what I want it to be, right? I want you guys to get smarter than me. Since I was biased with the concept of exponent that we are learning, I took the exponent approach and I converted this radical form to rational form, and then I did the calculation. And that was fine. There's nothing wrong with that. Because we got to practice it, relating it with the concept that we have learned. Since the power was same, this root was same, third root, both the cases, Pranit's approach will be much faster than the approach I took. But the advantage of what I did is that it will just help you recollect what we have done and how we can apply it as a generic rule of thumb. But now, since we are talking about how do we save time while solving problem, I would take Pranit's approach. So that is part of, see again, I brag about RAN, I did not apply RAN effectively. After reading the problem, I jumped onto this one. Because if I would have spent time here, I would have clearly seen that my root is matching. That means I'll multiply 2 and 2, that will give me 4. And then here cube root something, that means cube root of the whole thing. 4 cube root of 8, and 8 is nothing but 2 into 2 into 2. That is how you get a 2 from here. It will be much quicker, but then what I was doing before, that is your generic approach for solving any type of problem relating to radical components when the roots are different. If the roots are same, this is your shortcut. And keep both the options in your back pocket. Don't get going in the way I did, because that will work fine when the roots are different. When the roots are same, you certainly don't want to explore all the exponent roots. Yeah? Does that sound okay to everybody? Riya, Yasmita, Vivan, Jenna, everybody? Neil, Sarah? Okay. Now time for exercise. Who all can do somersault? Anybody here in the class who has done enough gymnastics before? Anybody? Nobody's from track and field, is it? Or gymnastics? Okay. Okay, I'm not asking anybody to do somersault here, okay? My math class. This is what we will just see. If I have 5 to the power 2, everybody is happy about dealing with this. If I have 5 to the power minus 2, what exactly is he talking about? How much that would be? Any number to the power, this is again an exponent, but with a negative exponent. So we call it negative exponent. When your power, see, when we have power as rational number, we call it rational exponent. Yes, Jenna?
Would it be 1 over 5 to the power of 2?
Yep. And can you describe that to the rest of the class? Why? How?
Why? I don't know why. I just know.
Okay. Anybody else who wants to give it a shot? We have just 3 more minutes. I want to make sure that the promise I made about gymnastics, we do that gymnastics. Okay, so let me deal with it. If you have, let's say this time I'm changing the number, 7 to the power 3, you are talking about 7 into 7 into 7. No, nothing to worry about. But if I have same thing to the power minus 3, Jana said that it becomes 1 over 7 to the power 3, and that is right. Nothing wrong with that. But let's convince ourselves mathematically. If I have 7 to the power minus 3, that is as good as saying 7 to the power 0 minus 3. Correct? Can I say so? Yes, Smita, what do you think, Mita? Is that okay to say so? If I have 7 to the power minus 3, can I say 7 to the power 0 minus 3? I want to hear a yes from Yasmita, Riya, Vishal, Neil, Sarah, anybody, Ananya. Minus 5 is as good as 0 minus 5. Minus 12 is as good as 0 minus 12. Yeah? Agreeable? At least one yes, one like. No subscribe, only like. Minus 2 is as good as 0 minus 2, correct? Too many likes. Okay. Alright. No, I will see again. That's my bad habit. What to do better. I don't feel like moving on without getting a consent from everybody. So when I have this, I can write this as 7 plus 0 minus 3. Now let's go back to our second rule of exponent, which says x to the power a divided by x to the power b equals x to the power a minus b. Or if I think of it in a reverse way, I can as well say x to the power a minus b equals x to the power a divided by x to the power b. Correct? I just flip that equation. Yeah? Now what do I have? Something power something minus something. Something to power something minus something will be something to power this divided by something to power this. So this became 7 to the power 0 divided by 7 to the power 3. Any number to the power 0 is only 1. So this became 1. Okay. So if that means, look at this, 7 to the power minus 3, I can write this as 7 to the power 0 minus 3. And that relates to this second rule of exponent that we learned today. So that will be, so if I have something to power something minus something, that will be something to power something divided by something to power something. That's how, whatever Jenna said, I tried justifying it because I agreed to her answer. Do you guys see? Are you guys able to relate to what I'm saying? Yeah? So, summary of that, the exercise that I was talking about was, it flips. If you have anything to the power anything, if you move it from numerator to denominator or denominator to numerator, the sign changes. If tomorrow if I say 10 to the power 12, I want to write it like a fraction, it will become 1 over 10 to the power minus 12. This is the gymnastics exercise I was talking about. Because now look at this. When you want to move this guy up, it will change its sign. It moves as is. Look at this entry. Okay. Any number. So tomorrow if I say, let me give you guys a lame example. 5 to the power minus 2 times 5 to the power 3 divided by 5 to the power 4. You will say, let me put everything in one place. So this guy goes up. So 5 to the power minus 2 into 5 to the power 3 into 5 to the power minus 4. Everything is in one place now. When I am multiplying 3 exponents, what happens? My power gets added. So minus 2 plus 3 minus 4. Whatever is the power, that gets added simply. Now whatever you have, this is minus 2, minus 4, minus 6 plus 3. So this is minus 3. So this is 5 to the power minus 3. You can as well get rid of the sign and say this is my answer. Yeah? So just to summarize, we talked about, we did a recap of what are the rules of exponents that we had learned a long time ago. And then we said that okay, if those are the rules of exponent, that applies as well for other types of exponents also, which we sometimes term as rational exponents or radical exponents. Because exponent rules are generic in nature. Regardless of the type of exponents you are dealing with, you can apply those rules. And then we looked at what is rational exponents. When you have exponent which has power in the form of a rational number. And magically, we derived a term decimal exponents, which you will never come across. But it was just a little thing. Okay. Again, we are not going to copyright it as our group thing. But summary of that is, depending on whatever power you have, you can still apply the same rule of exponents as long as you see the base remains the same. And then we looked at what is a negative exponent, where we saw how this thing traverses. So don't learn this as a thing to memorize. Look at this as an opportunity to play with numbers. You are literally playing with numbers. If somebody like me is playing with this at this age, you guys are way younger to play with this for sure. Okay? So we'll look at this as a playful opportunity. And then we just applied some certain some of those rules for solving few problems. We did not solve enough problems today. In tomorrow's class, we'll solve more problems and look at how these concepts that we learned today or revised today is going to come into application in the class tomorrow. Okay? So all the kids who could not join today, I would assume they would join tomorrow, because Samriddhi and Parth, they both told me that they will join tomorrow. Today they had a conflict. And some of the kids who could not wake up on time because of my mistake, they'll have to watch the video and we'll meet again tomorrow. Alright? Tomorrow is going to be a more rigorous exercise for us to solve few problems. Okay? Alright? Have fun. Bye bye. Bye bye. Bye bye. Bye bye.